Welcome to another VCE Physics coaching video. My name is Philip Noonan, and today we're looking at the first area of study still in Unit 3. We've been looking at force fields, and we've been looking at gravity. Today we're moving on into the next one, electric force fields. It says electric force formulas here, and we'll start off with the 5 key formulas. Just remember, at your school might start with area of study 3, like dealing with motion, and then circle back to the first area of study. But we're just doing the areas of study in order. And you know what? The examination tends to have the questions in order too. So that's the way we are doing them. So first thing is, I've just noticed that there are 5 key formulas. I remember there was one table in the Hydrolo textbook I thought was very useful, and I've based this lesson, if you like, or this page on that. So in terms of where to start, I might just differentiate that the area around the force field is the area around a charged object that other objects that are charged can experience a force. So we'll look at non-uniform perhaps first on the right. There's uniform and non-uniform fields. So there's a diagram, if you like, of what the field looks like. You can see it's getting weaker because the spaces are getting greater between the field lines. So that's the electric field strength formula. So K is Coulomb's constant, 8.99 by 10 to the 9 Newton meter squared per Coulomb squared. And R is the distance we are away from the charge, and Q is the charge in coulombs. For an electron or a proton, the charge is 1.6 by 10 to the minus 19 coulomb. That's in the formula sheet, but it's one we might remember. You'll notice for the force between 2 charges, it's very similar to the gravitational force in terms of the formula. Okay, so a formula for the electric field strength of a uniform field, that's usually the field between 2 parallel plates. So it might be charged on the top, for example, with a positive charge, and on the bottom with a negative charge. The strength is the voltage divided by the separation. And we might do a quick example of that. Let's calculate it now. So the electric field strength for the uniform field is V over D. Might even just put that in. Always quote the formula if you can. So that's, let's say it's 1,000 volts and the separation is 10 centimeters. That means we've got 1,000, but if we convert that to meters, that's over 0.1. So that's 1.0. If I make it 2 figures, because the 10 centimeters is 2 figures, by 10 to the 4. Now that would be either volts per meter or newtons per coulomb you could equally put as well. So there you go. I've done an example of a question that we might receive sometime. Right, so in general, whether the force field is uniform or non-uniform, this central formula, F equals QE, is a bit like with gravity, W equals mg. It's a bit like that. I'm just writing compare that to W, or the force due to gravity, let's say, is equal to mg. So there's that's 3 formulas now, or 4 I should say, including the E equals V over D. And then the last thing I want to look at is if an electron is accelerating by the field, then work is being done on the charge. And remember, the direction of a field is the direction that a test positive charge would experience a force. So this positive would be repelled by the upper plate, so it would be accelerated down. So we define the field to be down. Similarly here, if I had a test positive charge here, it would experience a force away, being repelled from the other positive charge, therefore the field is out. So if work done equals force times distance, well, that's QE times D, just incorporating that formula there. But the D's cancel, you notice here, which means the work done, which is the increase in kinetic energy or decrease, if it's the force is decelerating the charge, it's equal to QV. So at the end of the day, it's dependent only on the voltage. In fact, we design a new unit of energy called the electron volt, where 1 electron volt is the kinetic energy of an electron accelerated by 1 volt. But we can take it a step further and come up with other formulas too that don't necessarily appear on the VCAA study design. And if we let QV equal a half mv squared, which is the energy, kinetic energy formula, we can rearrange that to get these two formulas here. All right, and they do get used from time to time with problems we'll encounter and that may be asked in the examination. Just a pro tip here, that V stands for speed at lowercase v, and just clearly make sure that's an uppercase V for the voltage on the plate, all right? Just notice how we're just slowing down even now, the way we're talking about it and having an awareness. We're going to do a practice example. What would be the speed of an electron accelerated by a 1000 volt potential difference in a uniform field that we've just calculated above? So V in that case would equal to, so set up the formula. So, well, I'll put in 2, I'm using this formula here, times 1.6 by 10 to the minus 19 coulombs times 1000 volts. I'll just extend that a little bit. And the mass of the electron, which is in the formula sheet, but you can remember it with time, 9.1 by 10 to the minus 31 kilograms. And if you run that through your calculator, that should come out to 1 to 2 significant figures, 1.9 by 10 to the 7, and it'll be meters per second, which is a very high speed. Just a note that you can't make the voltage even bigger, say up to giga electron volts, and make the electron go past the speed of light. That's a natural barrier, which we'll study more in Unit 3. So that's another type of question that we might get. And there is just one more, very quickly. Well, it'll be 7 minutes in. I'm going to draw the field line shapes for electric fields. Just in blue over here, I'll do it for the negative case. So rules for drawing field lines: make sure that they terminate and touch the charge itself and that they're at 90 degrees. All right, and typically you can draw 8. All right, and for a positive, a test positive charge here would be going inward. So here the lines go inward. I'm going to quickly draw 2 situations. One, if we've got unlike charges. Notice I'm making these a little bit bigger, so I'll make it positive and negative. So the field goes, the direction of a test positive would go that way. So cross that way. And I'll draw, you can draw 8 on each side. And so they'll tend to, that one will go there. This one, they don't have to go all the way around. So we're sometimes asked to draw these from scratch in an examination, or we might be given some samples for multiple choice. All right, so then just with care, put the directions in, just making sure I've got the direction going in the right way. And that will be positive. All right, yeah, oftentimes these are multiple choice, as I mentioned. All right, just casting an eye over that. I've done this quite a few times. I encourage you to stay right to the end of this video because I've got something very important to say about these diagrams and producing them from scratch in general, but I'll quickly draw the situation where we've got 2 like charges. So I'm going to draw just 14 lines in total here, and these lines will repel each other. So these ones will go something like that. And then I'll do this one's here. They'll repel each other. And then, so they'll all be positive. The field lines will all go out because they're positive charges. And a test positive charge will be repelled. Here I've got a total of probably 16 lines. Here I've got 14 lines. Now I want to mention something very important. How long we've been going? About almost, well, 10 minutes, but I'll push on. Notice how I've drawn all of these lines, drawings from scratch. Notice how I could probably draw all those formulas from scratch. Rather than write these formulas once, and this particularly the diagrams once on your A3 summary sheet and just leave it until the examination, I encourage you to see if you can regenerate this material just from memory more often than not. So that then the real skill is learning how to apply the formulas to novel or exotic type questions. And there was one on last year's exam 2022 in section A, which was a little bit of a challenging one that required a bit of thinking and a bit of mathematics. So yeah, being able to generate the material from scratch rather than pile it all into an A3 sheet at the end of the year is a better skill. So that's a very quick tour through electric force fields, just 10 minutes. It could take several hours to do, or many hours to probably complete, anything up to 20 hours to complete a whole chapter on the electric forces. But this is a basic introduction. I hope it serves you. And if you've got any comments about the video, please leave them in the comment section or subscribe to be made aware of any future videos. If you'd like any coaching to get an exercise on this completed or to have a complete run through again and some more sample questions, contact me to discuss some individual or even group coaching for VCE Physics. In the meantime, thank you very much for watching another VCE Physics coaching video.